So, hi everyone. Today I'm going to be presenting this paper, DETR. Uh, DETR spits yolos on real-time object detection. So, this paper is originally on arXiv. It's not published yet, but because of its speed and score, I decided to work on it, and I'm presenting it today because of that reason. So, as I said earlier, um, this paper is uh, beat, beating all the object detection model in terms of scores, in terms of AP in Coco dataset, also in terms of speed to in also Coco dataset, it's also faster than YOLO, all the other YOLO models, and also more accurate than other Dyna-based model. So, what are the main contributions of this paper? So, this paper first proposed a version of a DETR which can be used in real time, and it also state of the art for both speed and accuracy, as it's using transformers, so it doesn't require NMS, and so it doesn't require any post processing. And this paper mainly introduced an encoder, which they call a hybrid encoder, which efficiently can process a multi-scale features by decoupling intra-scale interaction and cross-scale fusion. So because of that, it's more efficient and also can catch features much better compared to other encoders, and while processing much less data. And it also proposes a novel query selection method, which they call is IU aware query selection method, which improves performance by providing high quality initial object queries to the decoder. So, and it also achieves accuracy improvements and speed improvements compared to yellow detectors and a dyno-deformable DETR for ResNet 50. So for ResNet, for dyno-deformable, it beats in accuracy and of course speed, and for yellow, it beats in the speed in high margin. So this is the overview of the architecture. So here the first pass through the image through a backbone. The backbone can be a ResNet 50 or ResNet 100, and then they take the feature layers. The, they take three feature layers, this S3, S4, and S5 of from the backbone, and then they send the S3 and S4 to this CCFM, which we'll see in more details later section, and then they send the S5, the layer S5 to AIFI transformer layer. It's AIFI is a transformer layer, which basically is a self-attention layer, which uh, creates the self-attention map between the high-level features of S5 and create a feature map which then also sent to CCFM, which fuse all the features from S3, S4, and F5 together, uh, and send it for query selection. And from after selecting query, they send it to decoder and detect the bounding boxes and classes. So this is the overview of the method. And so now let's dig a bit more deep into the paper. So in transformer, the biggest bottleneck is the encoder. So here in one research they found that the encoders is responsible for 49% of G-flops, but contributes only 11% of AP in deformable DTR. So it's more or less same in all the DTR versions. The data came out like scale DTR, conditional DTR. It's more or less same. The percentage is more or less same. For the G-flops suffers a lot because of encoder, but the AP increase because of the encoder is not much compared to the uh, speed suffer as compared to the G-flop decrease uh, it gets. So to solve this problem, they first try to break down the encoder into this A, B, C, D uh, design proposals. So to make this design proposal first, the from Dynor ResNet 50, they first removed whole transformer encoders from A, and rest are same. Like the concatenation of features and query selections are same as Dynor or ResNet 50. Uh, this is the first design choice. And for the next design choice, uh, they took one of the single scale encoder, which will take the feature from the backbones and then concatenate and then do the query selection. For the third proposal, they said they take a multi-scale encoder. So uh, just a second. So for the third stage, they took a multi-scale encoder. So where they took features from all the backbone layers. So in the backbone layers, they have this S3, S4, S5. So there are three layers are of different scales. S3 is one scale, S4 is one scale, S5 is another scale. So in single scale encoder, they just took one scale, most likely the last one, the S5. And for a multi-scale encoder, they took all the scales, for all the feature encoders feature layers features, and then they tried one. And for the fourth one, they combined both a single scale encoder and CSF, cross scale fusion. They fused all the features and made the query. So what this showed is here is that like when they uh, deleted the when they removed the encoder of a Dino ResNet 50, the accuracy was decreasing a bit, but the latency improved a lot. It's self-explanatory. They are removing the transformer layer for self-attention or multi-head attention or all. So which uh, which is responsible for this latency. In the second one, when they just use one scale single scale encoder, and then the accuracy improved, but the latency didn't increase much. Like it's 11.1. For the third one, where they have multi-scale encoder, so the accuracy improved further. So say it went to 43.43 AP to 45 when they used multi-scale. So that means if you use multi-scale features when creating the attention map, it is better for AP. And for the D, uh, for section D, uh, they took single scale features and fused with multi-scale features with CSM. So and then they got the most AP so far, and the latency is also increased in in the DS5. What they show later, they also discuss it later. Here, if for this AIFI module, which again we'll discuss later, but to give it a brief overview, what DS5 means. So, DS5 means when they're uh, taking feature in AIFI module, if they take all the features, which is this D, this D, if they take all the features, uh, the redundancy of features might cause decrease in performance and increase in computational computation. So For DS5, they just took this one layer and used it in AIFI module and created the feature F5 feature map, and then they fused all the features as 3S4 and F5 together with the CCFM module and uh, query created the query for decoder. So what they showed here is if they use just S5 for AIFI module, then the accuracy increases. So compared to D, the accuracy increased by zero point 0.4 AP, but the latency decreased a lot. Uh, so what they suggested is uh, don't take all the features for all the feature map for self attention. Uh, that will improve your performance in terms of latency and accuracy. So, and E is basically they combined all of them and made their own modification and get the highest AP. This is basically their own model. So we'll get into this in a later section. So this is the design of their encoder. I have touched on a bit for AIFI module. So what AIFI module is, AIFI module basically created to reduce the computational redundancy by performing intrascale interaction with only high level feature with richer semantic concepts. So as I said earlier, they just use this S5 to AIFI module to get the rich semantic concepts. And the AIFI module is basically a self-attention layer of a transformer. So the self-attention layer operation is applied to high-level feature to capture the connection between the conceptual entities in the image, which facilitates the object detection and recognition in subsequent models. Yeah. So it's self-explanatory. So the next one is also talked about is if we use all the features, uh, the if we use all lower level features, uh, which which might be unnecessary due to the lack of semantic concepts and the risk of duplication and confusion in introduction of higher level features. So one way of think about it is that like uh, the feature in S5 is coarse, which kind of also contain the feature from the feature map from S4 and S3. So if we use all of them together, this might create the redundancy and when creating the self-attention in transformer, it might create the confusion uh, which hampers the performance of uh, of uh, of the model. So to verify this, they tried with the two different modules as I seen earlier. This like in D, the accuracy decreased compared to the S5. So next, what is a CCFM module? A CCFM module is also taken from D, which where they basically try to fuse all the feature taken from S3, S4, and F5 together is using this architecture. So they take feature from all the layers and send it to a convolutional block, compared convolutional block, then they send it to a wrap block, and then they fuse together with the feature map of F5. So the process can be easily formulated using in this equation. So query key and value is equal to flatten 5 and flatten F5 is equal to ratio of attention Q F5. So what it basically means is we get the F5 from IFI, which is the self-attention layer, and we take F5, send it to CCFM, and fuse all the features, basically. So we have seen a wrap block here. So what is wrap block? So wrap block is a type of fusion block composed of convolutional layers. So it's just a convolutional network which fuse all the features, combines the features between uh, the layers, and yeah, so it's a fuse the just features, and it contains multiple repeating unit of convolutional layers. So they used a multiple. Uh, they said it's n number. So in the experiment, they it can be changed. So this number of convolution layers can be changed depending on the data set, depending on the experiment settings. And for the fusion, they used element-wise addition, and they send it for uh, IOU query selection method, and then after IOU query selection method, they send it for decoder. So what is IOU selection method? IOU selection method is uh, is the way to select the queries for a decoder uh, based on the bounding boxes and classification score. So uh, in decoder, normally what we do is we select a certain number of queries for any downstream tasks. So for detection, to optimize those query selection, uh, they proposed this IO query selection method where they said if they used this loss function where they added IOU information uh, in the classification score, uh, which also gives the information of bounding boxes of each classification, each objects in the picture, in the image, to the decoder in the query selection stage. So, which they say results in better quality queries. So, and also there in implementation study, they show their IUA query selection method shows leads into better AP compared to vanilla uh, query selection method. So, and this is the experiment result on Coco dataset. So here they are extremely fast compared to other methods. Even compared to your, it's 71, and they're at 108. It's comparatively really fast than other YOLO based model too, and also from a Dino based model, it's much faster. So in terms of accuracy too, they are uh, currently the state of the art for object detection in Kokomo dataset. Yeah. So yeah, that was it for me. Thank you for listening.